Greetings to everyone. My name is Andrei Victor SANDU, and I'm Associate Professor of the Gheorghe Asachi Technical University of Iași. I'm grateful to be here among you to share some knowledges. And first of all, I want to thank the organizer and especially Professor Hanaa HACHIMI for inviting me to join you today. We have a good collaboration between Romania and Morocco, and we hope after the pandemic that we'll be stronger and we'll be able to collaborate for our future development. I'll be presenting today our topic entitled Materials Characterization, but before this, just a few words about me. My name, as I told you at the beginning, Andrei Victor SANDU. I'm Associate Professor of the Gheorghe Asachi Technical University of Iași, Romania, and also Senior Researcher of National Institute for Research and Development for Environmental Protection. I am also the President of an NGO, Romanian Inventors Forum. It's an association that promotes innovation worldwide, and also visiting professor for University Malaysia Perlis. Due to this, I am also representative for Romania for IFIA, International Federation of Inventors Association, respectively WIPA, World Invention Intellectual Property Association. I am publishing editor of several journals and also guest editor in other MDPI journals. I am the organizer of EuroInvent, European Exhibition of Creativity and Innovation, that this year will be the 13th edition, together with ICIR, EuroInvent International Conference on Innovative Research, started in 2015. I have more than 200 published articles indexed in Web of Science with a Hirsch index 22, I believe now it's already 23, but those are only details. My fields are especially on material science, obtaining and characterization of new materials, focusing on alloys, composite, geopolymers, non-metallic materials, and so on, and their specific analysis of optical microscopy, SEM, FTIR, TG, DTA, colorimetry, and so on, and also the second topic on environmental science, materials and procedures for water and air treatment. Next to this, intellectual property, patent writing and designing, and so on. As I told you, I'm a publishing editor of International Journal of Conservation Science. This is indexed in Web of Science and Scopus, and also developing journal, European Journal of Material Science Engineering, indexed in several international databases. Feel free to contact me and submit articles for our journals. Now, let's get back to our main focus, the characterization techniques that can be classified in several options. Here we have the surface analysis, we have image analysis, organic analysis, structural, and respectively the physical properties. And as Albert Einstein said, the whole of science is nothing more than a refinement of everyday thinking. So keep that in your mind and focus more. Now let's understand a little bit the surface analytical techniques. First of all, we have to define what surface is. So generally, if we consider a depth of 10 angstrom, that is the surface. What is below this, it's already in structure and the support material. In general, there are 4 beams called electrons, ions, neutrons, and photons, and also other 4 fields like thermal, electrical, magnetic, and surface sonic waves that can be used as input probes. So in order to support our analysis. When we employ any of these 8 probes, they give a rise on emission or transmission or respectively scattering of 4 types of beams, except the magnetic field, and these are electrons, ions, neutrons, and photons. These particles carry information of the surface to a suitable detector, and the detector assembles the and counts those particles, the emitted intensity, and also can identify the chemical nature of the species emitted, depending on if we have ions, neutrals, and so on, according to their energy. And all of these 4 types of information on the emitted particles are used to develop better understanding of the surfaces that we study in there. As you can see here, a schematic representation of the model of the generating techniques. You can see you have the magnetic field, influencing the surface. We have the electrons bombing with the electron the surface and getting other information, applying an electrical field, applying neutrals, bombing with ions, other photons and so on, even so sonic surface waves or thermal influence. Also here, very interesting design of the most used techniques and their fields according to the range. You can see here on the 3D scale from X, Y range to Z range. You can see from nanometric scale, microns and millimeters, the same on here. You can see the most accurate is scanning probe microscopy. Then we have the scanning electron microscopy and profilometers and respectively the optical methods according to their capacity of getting results with high resolution. Now we have another question. If we go to quantitative surface analysis versus bulk analysis, because bulk is something, like general info, and when we go to quantitative, we must know exactly what we have in there. So there are two questions here that arise. First of all, what is it, the qualitative analysis, and how much of it is there? That's the quantitative analysis. So we can identify what compound is there. Yeah, that's qualitative. And then quantitative, how much of that compound is there? Yeah, and some examples here with some calculus. Okay, now, if we speak about quantities that we are dealing with, order of magnitude and estimations, we have here surface density of water molecules on the surface of a water drop as an example, and the thickness of film produced by drying one drop of a solution with concentration of 100 ppm at the surface of a coin, and so on. There are some examples here, like an experiment that can be applied. We can calculate all this just as an example, but we will not get very much details of this, but we will discuss here. So how we can define what is surface and what means thin film, because this is the questions, how to identify. As I said at the beginning, if we speak about some Armstrongs, then we can have a surface. For example, the Earth crust has 50 kilometers, which is extremely thin compared to the Earth diameter, which is 12,000 kilometers, right? So the paint layer or a galvanic coating, which is like 100 microns, it's thin compared to the substrate of a steel sheet. For example, if we paint this. So as you can see here as an example, we have the atoms with 0.1 nanometers, and then we have small molecules or monolayers, which is 1 nanometer. So now the chemistry is considered nano, and below would be considered surface, micro, and above is bulk or structure. Now we speak again about some classification methods for the surface analysis. Here we have analytical methods that can be destructive, respectively non-destructive, as we call NDTs. But for destructive, we first of all, it means that we affect that material. That means we will need to slice it, etch it, atomic chemical attack. Okay, we have scrubbing, we have laser ablation, ion beam, plasma sputtering. So that means our sample will be affected. So we could not apply this on any kind of samples. We must first identify what samples we have. Then we can see if we can destroy it. For example, if we have a jewel or something extremely expensive, we'll not be able to use a destructive method. So then we go for the non-destructive methods, like we call in situ probing. Then we have the human receptor. That means our naked eye, rarely used. We have the applying of electrons, the light, which has different spectrums from infrared, ultraviolet, and X-rays. Then we have the neutrons and alpha particles. All of this used for bombing, but without destroying the surface. As you can see the schematic here, the probe gets a feedback from the surface. Now, the second part of the surface analysis, then we could imply the chemical analysis. Then we get the information about the chemical composition. Some examples here, we have extraction followed by HPLC or gas chromatography with mass spectrometry of extracts. This is chemical, usually liquid or gas analysis. Then we have dissolution or selective etching followed by solution analysis. We have also surface titration with appropriate coupling agent and so on. Also, we have the physical one when we get the information about the physical properties, optical properties of thin films by reflectivity and ellipsometry, surface structure by electron microscopy, also surface roughness by interferometry or stylus profiling, and so on. Then we have the work functions of metals or any other semiconductors. Another classification, physico-chemical, when we get the information about the chemical composition based on measurement of specific physical properties. Then we have here the spectroscopic techniques, which is infrared, ISO, XPS, EDX, SIMS, RBS, GDOS, and so on. A lot of letters for usually implying the X-ray analysis and different other probes for this. And here a more detailed classification on this. We have the microscopy, which we could have the most basic one, the optical one, then the scanning electron microscope, and further in depth we have the transmission electron microscope, field ion microscope, scanning tunneling microscope, atomic force microscope, and X-ray diffraction topography. Depending on how the techniques involves is, the more complicated is to prepare the sample for the analysis. For example, if on a scanning electron microscope you can put almost any solid samples on a standard SEM, I'm speaking here. For TEM, for transmission electron microscope, the sample need to be well prepared and it's more complicated. Then when we speak about the spectroscopical techniques, we have a lot of them that help us understand the materials. We have EDX, the energy dispersive X-ray spectroscopy, wavelength dispersive X-ray spectroscopy, WDX. These two, EDX and WDX, are coupled with the SEM, with the scanning electrons. Then we have the X-ray diffraction, which is independent device. We have mass spectrometry, secondary ion mass spectrometry, electron energy loss spectroscopy, Auger electron spectroscopy, X-ray photoelectron, ultraviolet spectroscopy, thermoluminescence, and photoluminescence. You can see a lot of terms in here. But first of all, you need to know what's your material that you need to study, and then you can approach the exact techniques that will get you the results counted for you. If we go then for macroscopic technique, we refer here to physico-mechanical ones. And we have here mechanical testings that includes tensile, compressive, grip, fatigue, toughness, and hardness techniques. Then we have differential thermal analysis, dielectric thermal analysis, thermogravimetric analysis, impulse excitation, ultrasonic techniques, and so on. Just short here about the XPS, which is not very common to all of us. We have here the excitation by X-rays, so we are bumping with the X-rays, and the surface would get an excitation, and then our detector will analyze the relaxation by emitting from the photoelectron. So it's pure physics. I don't want to bother you so much for this. What is important for us to know for example, the application, we can identify the broad spectrum with identifying the elements. It's exactly the same like the EDS. Then we can analyze, detail the spectrum and make the quantification and so on. Now we have the databases and the devices that will do this automatically for us. 20 years ago, we had to evaluate each peak, each value manually to identify how much compound is in there and so on, which is very, very annoying for us today when we are in the light speed era. So we analyze this with our devices and computers, and we get results instantaneous almost. So the results are similar with the XPS, with the EDX. As you can see here, the EDX, we are bombing with the electrons depending on the energy, usually from 10 to 30 kilo electron volts, and then we get results via the secondary or the backscattered electrons, respectively the X-ray using the EDX, and then we get, as you can see here in the image, the SEM, the electronic image, and also the results with the EDX. We're jumping over here. Some example, the basic quantification for this kind of spectra, but these now, as I told you, are automatically evaluated by the computer. An image of an old TEM, as I told you, TEM is the most advanced techniques when we speak about microscopy. As in-depth analysis, we can go up to 0.1 nanometers. Some examples in here with some compounds on nanometric scale. So these are images taken with the transmission electron microscope. Then we have the atomic force microscopy, which is similar to profilometry, but this has a cantilever and a tip, which has a contact on the surface, and that tip is very sensitive, and when it crosses the surface, it makes the profiling and can measure also the friction. Also, we can measure the nanorheology of the samples and so on, depending on the type of analysis we do. As you can see here, some examples and the 3D profile obtained by the AFM. Now here we have a comparison of various analytical methods according to their capabilities. The techniques, we have the element that they can identify. So lithium can be, all elements above lithium can be identified by IASI. Again, as you can see, XPS is going lower to helium, SIMS even starting from hydrogen, air bias only from carbon, EDX from sodium and higher, but now there exists EDX with better results. Also GDOS starting from hydrogen, you can see the limit starts at 0.1% and goes even higher for SIMS to 0.0001. Max depth resolution, you can see very thin from 0.3 nanometers up to 1 millimeters. We have also lateral resolution and many other characteristics. So depending on what kind of results we need to obtain, how in depth, then we have to select the proper technique that we have here on the table. Now, few devices that I used to work on them. On the left corner here, you can see the optical microscope. This is an advanced one. It's a biological one, but it's adapted for material analysis. It has also reflection and transmission, also fluorescence images and polarized image, bright field, dark field. So we can adapt whatever surface we have, we can get proper results on this. On the right upper corner, we have a scanning electron microscope. I'm working on that microscope since 2007. When it was new, now it's already old one. This is built by Tescan, a Czech company, and it's coupled with the EDX. On the left down corner, we have the X-ray device that gets us the specific composition. And on the right corner, we have the optical profilometer, which is similar with the atomic force microscopy. That gets us the roughness of the surface and rugosity and so on. The same here, other devices. These are some that I used during my PhD stage. Here on the left corner, this is micro FTIR. So it's a microscope coupled with the FTIR infrared spectrometer. Normally on an FTIR spectrometer, we need to prepare the sample to emit this in gallium bromide, which is the transparent medium for the infrared light. But here, according to this device, because we have the microscope, we can put the sample directly under the microscope, not required to emit it in the bromide. So we can analyze direct on the samples without destroying. So transforming one technique from destructive technique to non-destructive technique. So for example, we are here using ancient paper or paintings or things that we cannot select sample or cut sample from it. So we analyze directly on this. This is a cell for the corrosion testing on the right upper corner. On the left corner, we have a tribometer that can measure us the friction or the adhesion of different layers on the surface. And here we measured with, we have a hydraulic press behind it. We could identify and evaluate here the friction on some layers that we lubricated for the industry. And if we saw back there the devices, we have here some examples of results on the. We have the optical microscopy. These are some phosphate layers that are used in the automotive industry in order to protect the steel sheets that we manufacture the car, to protect them from corrosion. And also we enhanced the lubrication of the surface in order when you draw, mechanical draw these sheets in not to destroy the surfaces. So if the lubrication is higher, then the protection will be higher for the corrosion. Also, on different types of optical images, we can get here some cells in bright field, phase contrast, polarized light, dark field, Hoffman modulation, so on. These are some filters adapted to the optical microscopy in order to get what we need in there. Also, what was easy to identify in cross-section, we had steel sheets deposited with the phosphate layers, and we could measure them after we put them in the resin and we sliced it on cross-section. We could measure exactly the thickness of the deposited layers. Here, as you can see, some examples. Also, some images of these types of phosphating. I obtained many types of phosphate coatings, some of them more compact, others not so compact. And here we have the surface topography, then the elemental mapping with iron, zinc, phosphorus, oxygen, and nickel. Also the DDX spectrum from where we could get the chemical analysis on different types of layers. Here we have the difference between the backscattered and the normal secondary electrons. As you can see here in the left-hand corner, the detector used the secondary electrons, and on the right we have the backscattered electrons. It's the same image, but different detector according to what we have to analyze. Sometimes secondary electrons get better image, sometimes the backscattered electron get better image. The backscattered electron help us to identify if the phases are different and get a better contrast on this. Another example in here, some interesting samples. These are anti-friction alloys. As you can see here, the left upper corner is anti-friction alloy. Also, the right corner is anti-friction alloy. That means you can see the shiny, the brighter particles in there are the harder component, and the rest, which is grayish, is the softer component. So that means when those metal parts get in contact, they get in contact only on the shiny surface. That means a way reducing the friction between them. And a soldering alloy, you can see here in the down part, that's a soldering alloy. It's their structure on the scanning electron composition. This is how we get results from the EDX on various type of composition. I made, for example, here I had like 16 samples obtained and made analysis for all of them. Some of them had nickel, some of them had cobalt, magnesium, bismuth, chrome, and so on, manganese, depending on the layer obtained. So we can have here, this is the elemental composition for this, but the EDX allows us to get mass plus percent or the elemental composition, depends what we require for our study. Then we go for the XRD samples when we get all the samples in there, and XRD allows us to get the compounds. If the EDX gets us the element, we have iron, zinc, and so on, XRD gets us the compounds, and usually when we get the chemical composition and we get the chemical structure for the phosphate, we have the main ingredient, it's called phospholate. This is a compound very important when we speak about the corrosion of the phosphate layers. Then we have the micro-IF here, when we get also the spectrums and we identify the compounds. So if we are not sure on XRD what compounds we have there, we can use also the infrared spectrometer to identify the compounds in there. Then we have the cell to identify the corrosion resistance, and we have here the Tafel curves of several deposited layer. We made the test on them, and then we evaluated the speed of the corrosion, which is measured in millimeters per year. And the best sample that we got here is X2 or S3, as we see here in the image. Another study that was done for the first time, we could corroborate the spectrums, the infrared spectrums of the layers before and after the corrosion. So in the future, we can evaluate from this use of the analysis, which layer could be better after corrosion, just using this kind of analysis. And then we have the optical profilometry, similar to the atomic force microscopy, when we can get, this is the topography, the micro topography of the layer obtained by us. We can identify the granulometry and the surface area, many interesting analyses. We are short in time. We have the tribology, where we could measure the time until our layer was destroyed. You can see here the drawing force to get better results. As you can see, the black, it means the steel sheet, the regular steel sheet. And after we deposited the lubricant layer, you can see the force required to deform these samples dropped by half. So that means a prolonged time of usage for the devices that we're using in there. And another few examples, organic analysis, but we are closing here. If you want more details on the surface analysis, you have the link that you can get in there. And I hope you enjoyed our short presentation, and looking forward to have you joining our exhibition EuroInvent or ICIR EuroInvent next year. Take care and see you soon.